1, 2, the negatives are in this direction here. But now look what I did. I subdivided each entire unit. Each one being 1, 2, 3. This is 1, that's 2. And I would like to represent this point right here. Well, what is that? Well, looks like we've split this up in 3 parts. So, parts of 3, and it looks like it's the 2nd part of 3 sections. So, I'm sure most people can recognize that to be 2/3. So fractions can be represented on a number line, and this is how it would look like. Just 2/3, and you put a point there. Now, how can we represent this fraction in decimal form? Well, put the 3 out there and 2's in here. Well, 3 doesn't fit into 2, so 0. So I'm going to tack on a 0 and put a decimal point right there. There's a decimal point right there. You say, well, how many 3 fits into 20? Well, 6 of those, 6 times. I'm going to do this, by the way, the American way of doing division. There's also European or Latin American way of doing long division. We'll probably say that for another lecture. Anyway, we're going to get 18. We subtract, we're going to get 2. And we tack on a 0 here, a 0 here. And guess what? We're going to keep getting 20, 20, 20, 20, 20. And we're going to keep getting 6, 6, 6, 6, 6, 6, 6 forever. That's interesting. What does that tell us? Well, we know 2/3 is a rational number because it can be represented by an integer divided by an integer, not 0. I can place it on a number line, but its decimal representation doesn't stop like 0.5 or 0.25 like we saw earlier. It never ends. And notice it's always 6, 6, 6, 6. Now, that always has to be the case. It has to be exactly the same number. Well, no. I can have another number, for example, 0.12120, 1212 forever. Or I can have, let's say, 357 forever. Okay? As long as it's a set number of repeating digits along the way, that's actually a rational number. Now, how can we represent these decimals in a more... Obviously, I can't write it forever. So the 0.666 forever can be represented with a bar on the calculator over the 6. And this number over here, I can represent that with a bar over 1, 2. This can be represented by 3, 5, 7, and a bar over the 3 numbers. And that just means the number repeats itself forever. And that, in a nutshell, is what the rational numbers are all about. Here's some examples of these. Okay? Right. At this time, let's break out calculators and learn a little bit about how to input our different types of numbers in here. Okay? So I have this mini cutout of the TI-84 plus over different calculator to illustrate this. First off, if you want to just type in natural numbers, all you really need to do is just type any of the number keys. That's pretty straightforward, pretty easy. Okay? If you want to include whole numbers, then make sure, of course, you count 0. Now, obviously, you use 0 for some natural numbers like 10. 1, 0. Okay. Integers would be the same thing, but we have an additional key to work with, and that would be the negation, negative key. Right down here. Now, big warning. Make sure you don't confuse this negation key with the subtraction key over here. Alright? They're different. If you get an error on the screen, syntax error, you press the wrong key. With rational numbers, what we're going to do is you can input all your number keys again, but also now you have your division key to represent fractions. So if I want to put, for example, 3 divide by 5 in the calculator, we'll just type in 3, divide by 5, and of course press enter. It's always a good habit to always actually also use the clear key that's up here to clear the display before you do your math operations. The answer for a rational number is always a decimal at first. We're going to learn how to convert fractions to decimals and decimals to fractions in more detail in the lesson that is titled Fractions. So we'll learn more about use the calc in that area at that point. Irrational numbers. So far we've looked at quite a few numbers. Natural numbers, whole numbers, integers, and rational numbers. There's another class of numbers. They're called the irrational numbers. Well, what are those? Well, those are numbers on the number line that cannot be represented by an integer divided by an integer. Okay. Well, what's an example? Well, the most famous example of an irrational number is pi. No, not that pi. What I mean by pi is this number, pi, the Greek letter pi. Well, what is that number? Well, that's the number that represents the number of diameters that fit on a circle. So if you have a circle right here, for example, and I have this diameter, okay, if I were able to take that out and twisted it and placed it right on the circumference of the circle, how many would fit? Well, approximately 1, 2, 3 diameters, but there's a little bit left right here. Okay, well, people have tried, well, not tried, they have measured this, and you get approximately 0.14 additional diameters right there. Okay. So someone asked, well, what's pi? I don't understand what pi is. Just the number of diameters that fit in a circle. Easy, right? Well, now that you know that, you can rest easily now. Well, great. How can I actually represent pi on the number line? Well, it's around, let's say, around right there. Okay. Now, I did not put the 0.3414. That's just an approximation. I want to say that's really the exact value of pi. So actually, irrational numbers can be represented exactly as a point on a number line. That's a fact. Okay? What's another example of an irrational number? Well, if you've encountered what I call radicals, like square roots, cube roots, most of those are irrational numbers. An example of that